Hello everyone and welcome. In our previous lecture, we have covered fundamental JavaScript data structure like array, string, object, map, and set. These are powerful tools built into the language. Today we are going to explore some common abstract data types and their underlying structure, the linked list, stack, and queue. Unlike array and object, which are directly available, these are often built using those fundamental types. Understanding them is crucial because they form the basis for many algorithms and more complex data structure you will encounter in programming. We won't be implementing them in detail today, but rather focusing on their concept, their rule, and their performance characteristics. Think of it like learning about different types of specialized containers. An array is a general purpose box. Today we will look at the chain of connected boxes, linked list, a stack of plates, stack, and a line at a store, queue. Each had a specific rule about how you can add or remove items which make them uniquely suited for certain problems. Let's start with the linked list. Imagine you have a treasure hunt, and each clue not only tells you something but also point you to a location of the next clue. That's essentially a linked list. Here is a conceptual look. A linked list is a collection of an element called nodes. Each node contains two main parts. The actual data it's storing, a reference or pointer to the next node in the sequence. The very first node is called the head, and the last node typically point to null or undefined, signifying the end of the list. Unlike array, which store elements in continuous memory location, linked list can have their nodes scattered anywhere in memory. They are connected purely by these pointers. This makes them dynamic. They can easily grow or shrink without needing to pre-allocate a large block of memory. Now let's talk about linked list common operation and their time complexity. Insertion and deletion at the head. If you want to add a new node at the beginning, you just create a new node, point it to the current head, and then make the new node the head. This is incredibly fast, a constant time big O1 operation. Similarly, removing the head is also big O1 operation. Accessing an element by position or value. To find the kth position element or element with a specific value, you have to start at the head and traverse the list, one node at a time, following the pointers until you reach your target. In the worst case, you might have to visit every one of n nodes. This makes access and big O(n) linear time operation. Insertion and deletion in the middle or at the tail. For these operations, you first need to find the node before the insertion or deletion point. Since finding a node is big O(n) operation, inserting or deleting anywhere also become an big O(n) operation, unless you have a pointer to the tail. Then inserting at the tail can be big O(1). Linked lists are particularly useful when you need frequent insertion or deletion at the beginning of a collection, or when you don't know the size of your data beforehand and want to avoid expensive reallocations. Next is the stack. Imagine a stack of plates in a cafeteria. When you add a new plate, you put it on top. When you take a plate, you take it from the top. This describes the LIFO principle, last in first out. Visually, it looks like this. A stack is an abstract data type that's supposed to primarily operation push that adds an element to the top of the stack. And second is pop that removes and returns the element from the top of the stack. You can also typically peek at the top element without removing it and check if the stack is empty. Stacks are often implemented using array or linked list internally, regardless of the underlying implementation. The interface, how you interact with it, follow the LIFO rule. The beauty of a stack is its simplicity and efficiency. Like post operation, adding an element to the top, if we are implementing this with the array, so adding to the end of an array. If you're implementing this with the help of linked list, then inserting at the head of a linked list is a constant time operation. Similarly, pop, removing the top element, if it is implemented by array, then removing from the end of an array. If it is implemented by linked list, then removing the head of a linked list is also a constant time operation. Peek, looking at the top element, is also big O1 operation. This big O1 performance for all core operations make stack incredibly efficient for their specific use cases. They are fantastic for managing tasks where the last action needs to be undone first, like undo redo functionality on an editor, or for handling function call sequence. Finally, we have the queue. Think of a line at a grocery store or people waiting for a bus. The first person to join the line is the first person to be served. This is the FIFO principle, first in, first out. Visually, it looks like this. A queue is an abstract data type that supports two primary operations. Enqueue, that adds an element to the back or rear of the queue. Dequeue, that removes and returns the element from the front of the queue. You can also peek at the front element without removing it and check if the queue is empty. Like stack, queue can be implemented using array or linked list. However, if using an array for a queue, shift removing from the beginning is an big O(n) operation, which would make dequeue operation inefficient. Therefore, queue are often implemented using a linked list or a specialized array-like structure to ensure efficient operation. Let's look at the time complexity for an efficient implemented queue. For enqueue, adding an element to the rear of the queue, if we are implementing with the help of array, or if we are implementing with the help of linked list, then tail of a linked list, if you maintain a tail pointer, is a constant time big O(n) operation. For dequeue, removing the element from the front of the queue, then removing from the head of the linked list is also constant time operation. Peek, looking at the front element, is also big O(n) operation. Queue are essential for managing tasks in order, such as processing requests, managing print jobs, or handling messages in an application. Okay, so where do we actually see these data structure in the real world of programming? Actually, everywhere. For linked list, like image viewer or music playlist, when you click next or previous in an image gallery or music player, it's very similar to traversing a linked list. Each image song is a node pointing to the next or previous node. Next, implementing other data structure. So linked lists are often used as the underlying structure for stack and queue when big O(n) operations are needed for both ends. Memory management. Operating system might use linked list to keep track of available memory blocks. For stack, undo redo functionality. In text editor or graphic design software, every action you take is posted onto the stack. When you hit undo, the last action is pop and reverse. Browser history. When you navigate to a new page, it's pushed onto a history stack. Clicking the back button pops the current page off, revealing the previous ones. Function call stack. When a program executes, functions are pushed onto a call stack. When a function returns its port off. This is how the computer keeps track of where to return to after a function completes. For queue, task scheduling and job processing. In operating system or web server, tasks or requests are often placed in a queue to be processed in the order they arrive. Think of a print queue when print jobs are processed one by one. Breadth first search, BFS. This is a fundamental algorithm for traverse graph network of interconnected nodes. BFS uses a queue to explore nodes level by level, ensuring that all neighbors at the current level are visited before moving to the next level. Messages queues. In distributed system, applications communicate by sending messages to a message queue. This ensures messages are processed in the order they were sent, even if the receiving system is temporarily offline. Alright, let's quickly recap. Today we explored three fundamental data structures that provide a specialized way to organize and access data. The linked list. The linked list is a chain of nodes, each pointing to the next. It offers great flexibility for insertion and deletion at the beginning big O 1, but require linear time big O n to access element or modify the middle or end. The stack follow the last in first out principle. It's like a stack of plates with operation like push and pop happening only at the top. All its core operations are highly efficient, running in constant time big O 1. The queue follow the first in first out principle. It's like a waiting line with in queue adding to the back and DQ removing from the front operation. With proper implementation, all its core operations are also constant time big O 1 operation. Understanding these abstract data types and their performance characteristics is vital. Even if JavaScript doesn't have them as built-in type like array, they are crucial patterns used to solve a wide range of programming challenges, from managing program flow to organizing complex data. That's all for today. I encourage you to think about problems you have encountered and how these data structure might offer elegant and efficient solutions. Thanks for watching.